Let's continue with the scientific mystery of erratic boulders and other clues of a very different Earth in the distant past. Some scientists believed a great flood had caused the strange landforms, observed both near and distant from glaciers. Others, like Charpentier, Schimper, and Agassiz, believed glaciers caused these geologic features. Agassiz thought glaciers once covered large areas of Europe. He said, "I conclude that at a certain epoch the whole of Europe was covered with ice. Death enveloped nature in its winding sheet." Pretty exciting stuff. Before these new claims could be accepted, more evidence was needed to support them. This is a good example of our claims and evidence way of teaching science. Agassiz toured Scotland, looking for evidence of previous glaciation there. He wanted to find evidence of glaciers far away from high mountains, where they no longer existed. Agassiz toured Scotland, looking for evidence of previous glaciation there. He found evidence of glaciers like this moraine far away from high mountains. Other scientists found similar examples in Sweden and France. A series of great debates ensued. Some scientists strongly supported the flood theory, others only the glacial theory. Agassiz recognized that seasonal melting of glaciers would produce considerable flooding, and adopted an explanation that allowed for both explanations. The major obstacle to adopting a glacial explanation was knowledge about climate change. Evidence was needed that the Earth had once been much colder. An explanation for how the energy of the system could change was also needed. In short, the geologists needed help from biologists, astronomers, physicists, and mathematicians. Scientists today use multidisciplinary teams to solve complex problems. We have found that a diverse group is better at solving tough problems, and that's why we encourage more girls and underrepresented minorities to study STEM fields. I'm really glad I could work this slide into my presentation. Evidence that the Earth cycled through warm and cold periods of time were soon provided by fossils, and later by ice and ocean sediment cores. During cold periods, plants and animals that were well adapted to cold weather could be found farther south in the northern hemisphere. Plants and animals that required warmer climates were found in limited areas or became extinct. Their fossils provided clues of both time and location, allowing scientists to map the extent of glaciation during different periods of time. But what could have caused these temperature changes? In 1875, James Kroll published Climate and Time in their Geological Relations. He included information on energy flow in his theory. Kroll thought ice ages could be explained by orbital eccentricity, the distance of the Earth from the Sun. This theory predicted ice ages would occur every 22,000 years, and that they would alternate between the northern and southern hemispheres. He realized that ice reflected more energy, but open water absorbed it. Thus, the idea of a positive ice albedo feedback was first recognized. In the late 1800s, before ice and ocean sediment cores, the timing of ice ages was not well understood. Kroll's theory was accepted for a time, then eventually disproved. But the need to consider changes in energy was at last recognized. Kroll's idea that changes in the eccentricity of our orbit would affect the amount of sunlight reaching the Earth, and thus the overall temperature of the Earth, seemed very logical. But it was too simple. Other changes influence our seasons, especially the Earth's tilt. But combining these effects was a huge mathematical task. It had to be done by hand, for there were no computers. Luckily, Milutin Milankovitch had the necessary skills. He was an applied mathematician at the University of Belgrade. But because he was a Serbian, he became a prisoner of war when Belgrade was captured by German and Austro-Hungarian troops. It was during this time that Milankovitch calculated the periods of the Earth's precession, obliquity, and eccentricity. Milankovitch calculated the amount of sunlight, or insolation, that would be received at 65 degrees north latitude. To do this, he separately calculated and graphed the amount of insolation for each of the three astronomical factors of eccentricity, obliquity, and precession versus time. He then added the factors together, just as physicists do with waves. You may have experienced wave addition if you have been in a boat when waves from two other boats made you bob up and down. First, you rise and fall a little from the first boat's waves. Then, when the waves from both boats reach you, you move up and down a lot. Milankovitch was using a mathematical process discovered by Joseph Fourier. Fourier was a mathematician who was part of the French Revolution, and he later traveled to Egypt with Napoleon Bonaparte. In addition to his mathematical work, Fourier published a theory of heat flow related to exchanges of energy between molecules. He calculated that the temperature of the Earth, based on its present distance from the Sun, should be much colder. He was the first to recognize that the Earth's atmosphere might act as an insulator, a blanket that trapped heat and kept temperatures somewhat steady between night and day. We now call this the greenhouse effect. If your students think math is dull and boring, you should have them learn about the life of Joseph Fourier. You may already know that the Earth's orbital path around the Sun is an ellipse, or oval, instead of a circle. This was discovered by Johannes Kepler. His evidence came from observations of the planet Mars, another example of claims and evidence. But the Sun is not the only large body whose gravity affects the orbits of planets. Jupiter, Saturn, and Uranus all pull on the Earth, causing our elliptical path to vary. Our seasons are caused by the tilt of the Earth. The amount of the tilt changes over time, primarily due to its spinning and the pull of the Sun and Moon. This is called obliquity. The surprising thing about the change in obliquity is that it also changes the locations of the Arctic and Antarctic circles and tropics of Cancer and Capricorn. A monument marking the location of the tropic in Taiwan in 1908 is now more than a kilometer too far north. Precession, the wobbling of the Earth's axis, was discovered by the Greek astronomer Hipparchus in about 200 BC, when he compared the position of the stars on the equinoxes of his time with those on charts that were 150 years older. Perhaps one of the earliest examples of claims and evidence. Sometime in the future, Polaris will no longer be our North Star. It will be Vega. Precession is due to both the spinning and the fatness of the Earth. Earth has a bulge at the equator, and the Sun and Moon's gravity shifts our axis of spin. You'll see this in the next module when I show you a spinning top. This concludes our lesson. Your assignments are to watch the next module, showing how you can illustrate Milankovitch cycles to your students, do the assigned activity, and take the quiz.